Hi everyone, my name is Fengxu. In this video, I will talk about our study, Real-Time Finger Force Prediction while Parallel Convolutional Neural Networks, a preliminary study. The accurate estimation of individual finger forces is a crucial part of the precise control of an assistive device. There are currently several approaches attempting to address this question. First is pattern recognition of EMG features to classify gestures, such as the figure below. The input are several channels of EMG recordings. Features were extracted and used by classifiers, such as SVM or LDA, for the gesture prediction. It is easy to implement, but the outcome is discrete, unstable, and not generalizable. An alternative option is to do population coding based on spike sorting. This approach is accurate and continuous, but is inefficient somehow. The high-density EMG signals were decomposed using a fast Ica-Based method to get the spike trains corresponding to individual motor units. The spike trains were summed up to predict the force output. In that process, the information of individual motor units were lost. Due to these limitations, we investigated the CNN model for direct population neural coding output using features extracted from the HD-EMG. The HD-EMG data were collected using a 8x20 HD-EMG electrode array to record the EDC muscle activity. To record individual finger extension forces, the index, middle, and ring fingers were respectively secured to 4 miniature load cells. During the data acquisition period, the subjects were requested to perform isometric finger extension and followed a preset target trajectory ranging from 0 to 40% MVC after the MVC has been measured for individual fingers. We calculated the two features within the sliding window. The length of the sliding window was 64 samples, and the step length was 16 samples. First, we calculated the feature of frequency spectrum maps using Fourier transform, including all the sampled EMG points within the window for each channel. As the spectrum was calculated channel-wise, there were 160 spectrum vectors within a single window. Then, we calculated the feature of energy heat maps based on the mean square value within the window of each channel. As a result, the dimension of the energy heat map feature was 8x20 for a single window. This example video shows the two extracted features change correlated with the measured force over time. Both the frequency spectrum and the energy heat map were stacked using 5 consecutive windows into 3-dimensional matrix. The figure shows the proposed parallel convolutional neural networks model for finger force prediction. The upper part of panel A illustrates the energy heat map feature and the frequency spectrum feature from 5 consecutive windows. The panel B shows the two pathways of CNNs with kernel sizes indicated in the blocks. The upper pathway extracted high-level representations from the feature of energy heat maps. The lower pathway extracted high-level representations from the feature of frequency spectrum maps. Each convolutional layer was followed by a max pool module and activated by the ReLU function. In panel C, the extracted representations were viewed as a feature vector and were fed into the fully connected layers. The number of neurons of the output layer was set to 8. Therefore, a higher discharge frequency that close to the class 7 represented a higher force level, while a low discharge frequency that close to the class 0 indicated a lower force level. We calculated the ground truth of composite firing frequency as the target of the CNN using the fast Ica-based decomposition algorithm. The output of the algorithm was the binary firing events of individual motor units. The composite firing frequency was then calculated by summing up the firing events of all the obtained motor units. A linear regression model was used to predict the force based on the estimated discharge frequency. We evaluated two conditions for the CNN-based method. The first is the same finger condition, where the training, validation, and the test epochs were 25 seconds of non-overlapped raw data, randomly chosen from a 5-minute trial for the index, middle, and ring fingers respectively. We also evaluated our model for the cross-finger condition, where the 25-second training epochs were from a particular finger, but the validation and test epochs were from a different finger. We compared our method with two different approaches. First is the fast ICA-based method. The firing event training of a single motor unit was obtained through spike sorting, in both offline and online manner. We also compared with the standard EMG amplitude-based method, which was obtained as the root mean square of the EMG signals. The criteria was the correlation coefficient between the measured force and the estimated force by three methods. An example force prediction is shown in Figure 3. The prediction by the CNN-based model is in the same finger condition as mentioned in previous slide. Shown in Figure 4, we averaged the results across 3 subjects and all fingers for each subject. It showed that the CNN-based method of 92% of correlation coefficient achieved similar performance compared with the fast ICA-based method of 89%, and both showed better performance than the EMG amplitude-based method of 81%. The CNN method also showed a higher correlation coefficient than the online calculation of the fast ICA-based method of 82% of correlation coefficient. Specifically, the CNN-based method achieved higher correlation coefficients in the same finger conditions than the cross-finger conditions. The current study developed a continuous and finger generalizable force prediction method based on parallel CNNs. The input data for the CNN were the frequency spectrum map and energy heat map features. We then used the model to estimate populational motor unit discharge frequency. Convolution with kernels explores the spatial-temporal relation of the energy map feature, while it also explores the correlation among frequency and time series in the frequency spectrum map. Additionally, a key setting of our model is that the discharge frequency is set as the training target of CNN, instead of directly training on forces. Because the training on the discharge frequency can enable the model to be generalizable to other tasks, such as the prediction of individual finger flexion forces or finger joint angles. In conclusion, we developed a novel approach for the real-time prediction of individual finger extension forces using a CNN-based model. Our method outperforms the fast ICA-based method in terms of generalizability across fingers, and is more accurate compared with the conventional EMG amplitude-based method. It is also efficient as decoding the population coding without spike sorting. There are several limitations on the developed method. First, we observed a low prediction accuracy of the discharge frequency in the near 0 and near 7 classes, or not following the measured force trace well in low MVC and high MVC regions. It may be caused by the similarity of feature patterns at such low or high force levels. Second, the performance of our model relies on the accuracy of the decomposition results of the fast ICA-based method.